Right, good morning. Okay, this will be your last lecture. We won't have a Zoom meeting on Friday because I'm going to be giving you your test. The test will be on sapling, and you'll have, it's open book, unproctored, and I'll announce when that's posted. Okay, your final exam, okay, I'm planning to post that on Top Hat. Okay, so today we'll review carboxylic acids and carboxylic acid derivatives. Okay, so this corresponds to it's chapter 13 and 14. Okay, so get out something to write with and some writing paper. First question is this. I have benzoic acid. And ethylamine. Okay, what is the product? Okay, you could also do the mechanism. The mechanism for this is actually very easy. It's an acid-base reaction. You remember that amines are basic, carboxylic acids are acidic. Okay, so the mechanism would involve a proton transfer. So oxygen is now negative. Nitrogen gains an H, so it becomes positive. All right, so we get a salt. Okay, so this would be ethyl ammonium benzoate. Okay, some of these salts, if you heat them, you can eliminate water. Okay, so two H's and an O. Which would give you an amide. Okay, this is an amide, this is an amine. Okay, there are actually better ways of making amides, as we'll see shortly. Okay, let's go ahead and turn to carboxylic acid derivatives, okay, which is chapter 14. start off with some nomenclature. Okay, so draw benzoic anhydride. Benzoic anhydride. Right, benzoic anhydride comes from benzoic acid. Anhydride means without water. So here is benzoic acid. Here is another benzoic acid. And if we split out water, right, this would be benzoic anhydride. Okay, this is a mixed anhydride. So draw ethanoic methanoic anhydride, also called acetic formic anhydride. Okay, so acetic acid or ethanoic acid is this. Formic acid or methanoic acid is this. And the anhydride look like this. Okay, this is actually a useful reagent. The formic acid part is quite a bit more reactive than the acetic acid part, and so you can make formate esters and formamides and other derivatives. For the next one, draw propanoyl chloride. Okay, propane is 3 carbons. Right, this is propanoic acid. And if we replace the OH with a Cl, then we have propanoyl chloride. Okay, this one's an ester. Isopropyl butanoate. isopropyl butanoate. Okay, the ending for an ester is ATE. Okay. Butane is 4. Okay, so butanoic acid would be this. If we replace the H with an isopropyl group, okay, so that is now isopropyl butanoate. N-ethyl N-methyl pentanamide. Pentane is 5. Okay, and okay, this is the amide group. Remember, the amide has a nitrogen next to a carbonyl. Okay, and these are the locations of the substituents. We have an ethyl, we have a methyl. Okay, so that's N-ethyl N-methyl pentanamide. Okay, this is an example of a tertiary amide. Okay, 3 bonds from nitrogen to carbon. Right, this is a salt. So draw the structure of potassium hexanoate. Okay, just like esters, salts will end at ATE. Right, hexane is 6. Okay, hexanoate is derived from hexanoic acid, which is this. Right, if we replace the H with a K, okay, this is potassium hexanoate. Right, most of the reactions of carboxylic acid derivatives either involve converting them into carboxylic acids or converting them into other derivatives. Okay, so for example, we have acetyl or ethanoyl chloride. Okay, acid chlorides are the most reactive, and they will hydrolyze even in the presence of water. Okay, this is the common mechanism. Okay, carbonyl is polarized, carbon end is plus. Okay, water acts as a nucleophile, comes in. pushes up onto the oxygen. Okay, oxygen, this oxygen now has a plus charge. Okay, so in all of these substitution mechanisms, we'll go through this tetrahedral intermediate. And because chloride is a good leaving group, oxygen pushes down and it expels the chloride. That makes this a double bond. Chloride's gone. Right, and then chloride, or you could have another water. Chloride removes a hydrogen. Okay, so we'll get acetic acid and HCl. So draw the mechanism and products for this. This will be almost exactly like what I just showed you with water. Just a different nucleophile. Okay, so this is our nucleophile. Comes in, attacks the carbonyl carbon. This oxygen, sorry, is now plus. Okay, oxygen moves down, kicks out the chloride. Right, and then Cl minus. Typically, you would use an organic base. Okay, maybe something like triethylamine to remove this hydrogen. All right, so our product would be cyclopentyl acetate or cyclopentyl ethanoate. Okay, so this is an example of forming a derivative from another derivative. We form an ester from an acid chloride. Okay, converting a derivative into another derivative works if we're going from a more reactive to a less reactive derivative. Okay, so the order of reactivity is acid chloride, most reactive, then anhydrides, right, then esters, and then amides. Amides are among the least reactive. And then carboxylate salts are even less reactive than amides. Here we're going to be converting an acyl chloride into an amide, and you'll need some kind of a base to neutralize the HCl. Sometimes what's done is just to use excess of the ammonia or amine that you're using. Okay, so this follows the same pattern. It's nucleophilic acyl substitution. Okay, so it comes in. Okay, and again, we expel the leaving group. Now double bond. Okay, and then we used 2 equivalents of ammonia. Okay, ammonia is a much stronger base than, it's a weak base, but it's a much stronger base than chloride. Okay, so the last step is an acid-base reaction. Okay, so our product would be benzamide, or systematically it's benzene carboxamide. Okay, but benzamide is accepted in the IUPAC. Okay, let's move on and look at some examples of reactions with anhydrides. We use acetic anhydride. Remember, anhydride means without water. Okay, this reaction is much slower than with an acid chloride. With an acid chloride, conversion of that compound to carboxylic acid and HCl with water takes only a few minutes. Okay, this may take, if you just mix it with water, okay, this may take weeks. Let's see, that's wrong. So we'll form 2 carboxylic acids from an anhydride. Okay, let's react acetic anhydride with phenol. Okay, what's the mechanism? Okay, this is just like the acid chloride, except you have a different leaving group. And typically for something like this, a base is added in order to remove the proton in the last step. Okay. Often what is used in forming esters is pyridine. Pyridine can serve as a base and as a solvent. Okay, this won't compete with your other nucleophiles. All right, so this will attack one side or the other. Since this is symmetric, it doesn't matter which side. Okay, so what's our leaving group? Well, it can't be methyl. Methyl is a really terrible leaving group. Could be the phenol, but that would just take you back to where you started. Okay, so what's going to get expelled is this group right here. Okay, and that's a good leaving group. It's a weak base. Okay, so that's the acetate ion. Okay, this becomes a double bond now. Okay, and you could also show this acetate removing the proton. Okay, so our products would be acetic or ethanoic acid and this would be phenyl acetate or phenyl ethanoate. Okay, what about the mechanism for reaction of acetic anhydride with diethylamine? Okay, what's the mechanism? Okay, it's just like the last couple we did. Okay, the nucleophile attacks one side or the other. Okay, just like with the ester, this moves down and it will kick out acetate. Okay, and experimentally, you probably add, you probably use excess diethylamine or some other base. Okay, but this could also remove the hydrogen. Okay, so we'll get acetic acid and we'll get and diethyl acetamide or ethanamide. Okay, so an anhydride will give a carboxylic acid as one of the byproducts. With water, you get 2 carboxylic acids. With an alcohol or phenol, you get an ester. With an amine, you get an amide. You can't use a tertiary amine. It has to be either ammonia or a primary or secondary amine. There has to be at least one H on the nitrogen to start with. All right, the next thing we're going to look at is hydrolysis. And hydrolysis means splitting with water. And I've already shown you hydrolysis of acid chlorides and anhydrides. That simply involves mixing the starting material with water. With esters and amides, however, hydrolysis usually requires a high temperature and either high or low pH. Okay, so if we have an ester, okay, this is ethyl butanoate. Okay, under acid conditions, okay, we'll split this ester. We'll get a carboxylic acid and an alcohol. Okay, under basic conditions, this is what we call saponification. Okay, but there's one difference, and that is this is under strongly basic conditions. This is acidic, and so this is going to remove this hydrogen. Okay, so under basic conditions, we'll actually get the carboxylate salt. This is a weaker acid than water, so you won't get the alkoxide salt, just the carboxylate. Right, amides can also be hydrolyzed. Since amides are less reactive, they require oftentimes a longer time to hydrolyze and a high temperature. Okay, so if we have for example, N-methyl butanamide, okay, under acidic conditions, Okay, of course, we'll get the carboxylic acid. This. Okay, since amines, the amine that would be produced is a base, we're carrying this out in acidic conditions, we'll get the conjugate acid. So we'll get the ammonium ion. In this case, the methyl ammonium ion. Right, under basic conditions, okay, this time we'll get the amine. But since carboxylic acids are acidic, we'll get the conjugate base. So we'll get the carboxylate, the butanoate ion. Right, nitriles are considered carboxylic acid derivatives because when we hydrolyze them, we get carboxylic acid. Okay, so under acidic conditions, we would get carboxylic acid, and we would also get the ammonium ion. Right, under basic conditions, okay, same products as we would get with an amide. So we would get the carboxylate, and we would get ammonia, NH3. Okay, and then the last couple of topics are reactions of esters with Grignards and reduction. All right, so if we have an ester, okay, this would be methyl propanoate. Okay, unlike aldehydes and ketones, this will react with two equivalents of Grignard. And it's actually the same mechanism. It starts off as the same mechanism as nucleophilic acyl substitution. Okay, let's use ethyl magnesium bromide. Okay, carbonyl is polarized, carbon end is plus. Nucleophile attacks the carbon nucleus. So we've added an ethyl to this position. Okay, but we don't protonate it at this stage because that would give us a hemiacetal. Most hemiacetals are not stable. Hemiacetal, remember, that's where we have an alcohol and an ether on the same carbon. Okay, so what happens, okay, just like in the, say the reaction with an anhydride. Oxygen pushes toward the carbon, expels the OCH3 minus. Okay, now we've got a ketone. Okay, we saw in the chapter on aldehydes and ketones that ketones will also react with the Grignard. Okay, so don't use this same Grignard to attack. Draw another one. Okay, so this will attack the carbonyl. All right, and then when this reaction is complete, we add dilute acid. All right, and this would be our final product. Okay, so this is 3-ethyl 3-pentanol. Okay, and then lithium aluminum hydride will reduce carboxylic acids and esters and acid chlorides. We typically wouldn't use an acid chloride. It will convert all of these to a primary alcohol. Okay, an amide would be reduced to an amine. Okay, so notice the oxygen is gone now. That's it for today. Okay, and I will notify you when the exam has been posted.